everyone. I hope you guys are doing well. First of all, I would like to thank all of you for the support you've given to this channel. We've recently hit 1000 subscribers and I think that was a couple of days back only. So thank you for all the support, and I cannot express how happy I am to help all of you guys clear your concepts, and I see a lot of you cleared the exams as well watching these videos. So thank you for all the support, and I'll keep posting videos so that it helps you. So now a lot of people have asked me to make videos on navigation. But what I feel is that navigation is something which should be taught, and it is better understood when someone's teaching it to you physically or practically. But because of the pandemic, everything is virtual now. So I'll try my best. I'll post some videos and it's up to you. You guys tell me if those are helpful or not. I'll try my best to teach the concepts properly. I'll try my best to be as specific as possible. But what I need from you guys, especially in navigation, is a very good imagination. So if you can imagine what I'm teaching, for example, if I'm talking about latitudes and longitudes, so what I want you guys to imagine is a globe with lines running from the poles to poles and lines going around the equator towards the poles like this. So that's what I want you guys to imagine when I'm teaching for, say, the graticule. Because if your imagination is good, navigation is just a cakewalk for you. It is not difficult at all. Like I said in the previous videos as well, these exams are not difficult, it just depends on your concepts. So this is what I want from you guys, because since we won't be interacting physically, I cannot take a globe and show everything to you. So yeah, I'll try my best to put all this on a 2D screen and explain the concepts to you. So in this video, I'll be talking about the basics of general navigation. So thank you again, and let's dive into it. Okay, so let's start by talking about the shape of our planet Earth. Now, if you ask a layman about the shape of the Earth, he would definitely answer by saying that it's round. Okay, so there are a lot of people who believe that the Earth is not round. Yeah, seriously, I have literally talked to people who just refuse to believe the fact that our Earth is round. They believe it's flat, and they have their own logics and reason behind that. So if you're a flat earther, good for you, but in aviation, we believe that the Earth is round. And all our concepts are based around this fact. So yeah, Earth is round to us. Now a layman said that it's round. But if I want to get into a bit more specifics, so I can call it a sphere, right? Now if I want to get into a more specific term, I would call our planet an oblate spheroid or an ellipsoid. So this is what round is, this is what sphere is, and this is what an oblate spheroid is. So if you look at an oblate spheroid and compare it to the Earth, this is what the Earth is actually. Earth is flatter on the poles and it's bulging out on the equator. So from now, if anyone's gonna ask you about the shape of our planet, your answer should be an oblate spheroid or an ellipsoid. Okay, next. So we all know what a diameter is, right? It is a line passing through the center of a circle. Now for our planet, which is almost a sphere, this is what a diameter looks like. Now if we talk about the two diameters on our planet, one will be the equatorial diameter, which is the red one, and one will be the polar diameter, which is the green one. So as the name suggests, the equatorial diameter will be the diameter along the equator, which is the center of the Earth. And the polar diameter will be the diameter of the Earth along the poles. Okay, now what I said in the beginning of the video when I was talking about an oblate spheroid, I said that the Earth is flatter on the poles and it's bulging from the center. So that is why both of these diameters cannot be equal. Obviously, if the Earth is bulging on the center, the equatorial diameter will be more than the polar diameter. Because actually, if you want to imagine our Earth, you could draw it something like this. So this is a more exaggerated version. This is actually a very exaggerated version of our planet, but it helps understand this. So the equatorial diameter is along the equator. And obviously, since the Earth is bulging from the equator, it will be more than this polar diameter because the Earth is flatter on the poles. right? So if this diagram helps you, I want you to imagine this whenever you're talking about the diameters. So one is the polar diameter, its length is 6865 nautical miles, and one is the equatorial diameter, its length is 6888 nautical miles. If you look at the difference is 23 nautical miles between both the equators. So now after talking about the diameters, I can introduce ourselves to a term known as the compression ratio. So this is the ratio of the difference between these two diameters. So we saw that we have two diameters and both are different. So what is the difference between these? The ratio between the difference between these is the compression. So you see in this diagram that the earth is compressed. Now we have to find how much is this compression. Now to find the compression ratio, we use this formula. So it says the equatorial diameter minus polar diameter upon the equatorial diameter. Now if you remember, our equatorial diameter was 6888 and the polar diameter was 6865. So it will be 6888 minus 6865 upon 6888. So now if you solve it, it comes out to be 1 upon 297, which we can say is close to 1 upon 300. Right? So this is the compression of our earth. Now if I find it in percentage, so the compression ratio will be 0.3%. So this is the compression ratio of our planet, which is 1 by 300 or 0.3%. Okay, so this is the ratio by which our planet is compressed. Obviously it's compressed because we have a figure like this for our planet. So the compression ratio is 1 by 300 or 0.3%. Now in some videos what you'll find is that the equatorial diameter is referred to as the major axis of the earth and the polar diameter is known as the minor axis. So now if you find these two terms, don't get confused, it's just the polar and the equatorial diameter, just a different name. Perfect, so we've talked about the compression of our earth. Now let's talk about the rotation of our earth. Now how I remember this is again imagination and logic. So we know that the sun rises from the east, right? For everyone, for you, for me, the sun rises from the east. Okay, so what I do is I imagine a sun that is on the right of the earth. Okay, right means it's on the east of the earth. Perfect. Then I imagine myself standing over here on the earth, right? Wherever this is. Now I know that the sun rises from the east. Okay, it comes to my house from the east, right? Now what I know from general knowledge is that the sun is there and the earth is rotating. So if I see the sun coming from the east, that means my earth is moving that way, right? I was here, then I'll be probably here as the earth is rotating, right? So if I see the sun coming from the east, that means my earth is rotating from left to right. Yeah? So we can say that the earth is rotating from the west to the east. So this is how I remember it. I just imagine a sun on the right side and I know that the sun is coming to me. Now the sun cannot come to me logically, so I would go to the sun. And if I am going to the sun, that means that the earth is rotating from the left to the right. Perfect, which is from the west to the east. So this is the direction of rotation of the earth. Perfect, I hope this helps you. Next, I want you all to think of a globe. So if you've ever seen a globe, you would have noticed that the earth on a globe is always tilted, right? If you look at this diagram also, the earth is tilted. I go and buy a globe and he gives me a tilted globe. But this is not a defect. This is the actual representation of the earth. So if you look at the actual earth, which is the image on the right, so we can see that our earth is actually tilted by some degrees towards the right. So now how much is this degree? So it is 23.5 degrees. Okay, or 23.5 degrees. So our earth is tilted to the right at 23.5 degrees. Okay, so I don't know the reason for this tilt. No one ever taught it to me. But just out of curiosity and my interest in astronomy, I tried Googling it. I just Googled what is the reason behind the tilt of the earth. And it turns out that this tilt is still a mystery. There is no reason to it. No one knows the reason to it. Some people believe that something big hit the Earth when the planet was young and caused this 23.5 degree tilt in its axis. So it's still a mystery. No one knows the real reason. Now this is not required for you to know, obviously, because it's still a mystery. So what you should know is that the tilt is 23.5 degrees from the normal plane. Now this is the normal plane. And this tilt is 23.5 degrees from the normal plane. And if I talk about an orbital plane, so this is the orbital plane. So this tilt is 66.5 degrees from the orbital plane. So these are the two things which you should remember. So it is 23.5 degrees from the normal plane and 66.5 degrees from the orbital plane. Okay, obviously, because if you add both of these, it would come out to be 90 degrees, which it should be, right? Perfect. Now I'm quite sure you guys would have heard of these terms and you would probably know what these are. So before talking about these, I want to introduce two terms to you. First one is a great circle and the second term is a small circle. So a great circle is the largest possible circle that can be drawn on the surface of a sphere. So it would be of the same diameter as that of a sphere. It will be passing through the center of the sphere, and if we cut the sphere at a great circle, we will get two equal hemispheres. So now I want you to imagine and look at this figure as well. So this circle which you can see on the sphere is the biggest circle that is possible on the sphere. There cannot be a circle that is bigger than this. And like you can see in this figure, this circle cuts this sphere into two equal parts. So this is what we call a great circle. Now another property of a great circle is that it is the shortest distance between 2 points. So since it's a circle on a sphere, it will obviously be the shortest distance. Like in this diagram. If I was to go from P to Q, so if I want to go from this point to this point, and if I follow this path, the red path, this would be the shortest distance between P and Q, because this is a great circle distance. So now if I draw a great circle passing from Q to V, which is this great circle, and if I follow this path from Q to V, so this will be the shortest distance from Q to V. Now to understand this, I want you guys to imagine. So if you imagine 2 points on the globe and a line passing through them, right? Now if you continue that line throughout the globe and come back to the first point, that would be a great circle. So the shortest distance between 2 points is the great circle track, right? So now you guys know that a great circle will be the biggest circle inside a sphere. So if I talk about any other circle except for the great circle, it will be obviously smaller than the great circle, right? The great circle was the biggest circle in the sphere. So if I make any other circle inside that sphere, that will be a small circle. Small circle meaning that it is smaller than the great circle. So in this diagram, the yellow one is the small circle and the cyan or the blue one is the great circle. Small circle is nothing but it's just smaller than a great circle. Now if I make another circle over here, this is also smaller than the great circle, right? So this will also be a small circle. This will also be a small circle. This will also be a small circle. So any circle that is smaller than the great circle is a small circle. Perfect. So you'll understand it better when I give you examples. So now I want you to look at the equator. We know that this line is cutting the Earth into two equal halves, right? And the diameter of the equator is same as the sphere's diameter. So we can say that the equator is a great circle, right? Because this line is the biggest circle on the Earth, on the sphere. So equator is a great circle. Now I want you to start your imagination again and think about the number of great circles we can have on the Earth. So now I want you guys to pause the video right here and think about it. I want you to use your full imagination and think about how many great circles can we have on the planet. And once you get the answer, I want you to continue with the video because I've answered it right after this. So if you look at a sphere, it can be divided into two equal parts in a lot of ways. I can cut it this way, I can cut it this way, I can cut it this way, I can cut it in a lot of ways, and it will be two equal parts after cutting it in so many ways. So there can be infinite number of great circles on the earth, right? I can make a great circle like this, that will also be a great circle. I can make a great circle like this. This is also the biggest circle of the sphere. I can make a lot of great circles. All these circles you see in this diagram have the same diameter as that of the earth. They are the biggest circles of the sphere, and the center of the sphere is at the center of these circles as well, right? So I can have infinite number of great circles on the earth. Now another fact about great circles is that there can only be one great circle between 2 points, unless those points are diametrically opposite to each other. So if I take two random points on the earth, how many great circles do you think can I make on this, passing through these 2 points? The correct answer is just one. So I can make only one great circle that is passing through both of these points. Obviously it will go on the back side as well. I don't know how to draw a 3D image. So yeah, I hope you understand the point. So there can only be one great circle passing through 2 points on the earth. Now, if those 2 points are the 2 poles, so if this is one point and this is the other point, how many great circles can you think can pass through these 2 points now? Exactly. Like in this diagram, there are so many great circles passing through both of these points. So, this is also a great circle. This is also a great circle. This is also a great circle. This is another great circle. This is another great circle. Another one. Another one. Another one. One more. So there can be infinite number of great circles between two diametrically opposite points. Diametrically opposite means like the poles, which are literally opposite on the earth, right? So only one great circle passing through 2 points, and if those points are diametrically opposite, infinite number of great circles passing through them. Perfect, I hope that helps you. Now if I talk about more examples of great circles, they can be the meridians and the anti-meridians. So you know what a meridian or a longitude is, right? It is these black lines which you can see on this earth. Okay, now if I combine a meridian and its anti-meridian, anti-meridian is the meridian that is on the opposite side of the earth, which we cannot see. So if I combine a meridian and its anti-meridian, I'll get a great circle. So another example of a great circle is a meridian along with its anti-meridian. Now if I just talk about a meridian, so if I just talk about the red part and not its dotted line which I just drew, which was the anti-meridian. So this is known as a semi-great circle, which means a half great circle, right? Perfect. So now I'll give a brief about what are meridians. So meridians are the lines which are joining both the poles. A meridian is a semi-great circle, and a meridian along with its anti-meridian is a great circle. Now we have a datum meridian which passes through a place called Greenwich, and this meridian is known as the prime meridian. So in this diagram, this black line, which is now the yellow line, is the datum meridian or the prime meridian. Now all the meridians east of the prime meridian are called east, and all the meridians west of the prime meridian are named west. So for example, in this diagram we can see that we have the 30 degrees east, 60 degrees east, 90 degrees east, 120 degrees east, 150 degrees east, and similarly on the left side or on the west side we have 30 degrees west, 60 degrees west, 90 degree west, 120 degree west, and 150 degree west. Now what is the maximum these meridians can be? So the maximum they can go is 180 degrees east or west. So the maximum meridian can be 180 degree east or west, and these degrees are from the prime meridian. So this line is 30 degrees from the prime meridian. this line is 90 degrees from the prime meridian. And since it's to the east of the prime meridian, we call it 90 degrees east longitude. Okay, and the prime meridian, which I drew with the yellow in the beginning, this prime meridian is named as 0 degrees east or west. So this is 0 degrees and this is the datum. So it goes to the right and to the left, and right behind the prime meridian, the anti-meridian is 180 degrees east and west, because obviously that is the maximum that it will. Perfect. Now let's look at examples of small circles. So any circle which is not a great circle is a small circle. Now if you look at this sphere, and if someone asks you what is the great circle in this, so I can guess. So obviously you cannot tell exactly, but you can guess that this is the great circle of this sphere. So you can guess that this is the great circle of this sphere, because I can see that this is the biggest circle of this sphere. I may be wrong, but it looks like it's the biggest to me. So this is the great circle, and all the circles except for this one are the small circles. So all of these are small circles, right? All of these are small circles and the yellow one is the great circle. Perfect. So all these green ones are latitudes. I know we've heard of this term a lot. So these are latitudes. So latitudes are the horizontal lines which are on both sides of the equator. So for latitudes, the datum is the equator. We have latitudes north of the equator and we have latitudes south of the equator. These latitudes are called north when they're north of the equator and are called south when they're south of the equator. So if you look at this diagram again, we have a 30 degree north latitude, 60 degree north latitude and a 90 degree north latitude. And we have a 30 degree south latitude, 60 degree south latitude and a 90 degree south latitude. Now these degrees are again from the datum. The datum here is the equator. Now I feel like telling you how they've measured this 30 degrees. So they take a line from this 30 degree point and join it to the center of the earth. Then they compare it to the equator and see that what angle is it making with the equator. So this will be 30 degrees. Now if I talk about the poles, if they take a point on the poles, let's say if this is the point, and they join it to the center of the earth, then compare it with the equator. So what do you think will be the angle? Obviously, yes, it will be 90 degrees. So 90 degrees is the maximum that a latitude can be. So the North Pole is 90 degree north latitude, South Pole is 90 degrees south latitude. Okay, I hope this diagram helps you. Next, if I look at the globe, it has both the latitudes and the longitudes. Longitudes are also known as meridians and latitudes are also known as parallels. So the combination of both the latitudes and the longitude, or the meridians and the parallels, the grid that we get is known as a graticule. So graticule is the grid that we get. So the network of latitudes and longitudes is known as a graticule. Perfect. Now let's talk about what is a rhumb line. So a line on the surface of the earth that cuts all the meridians at the same angle is known as a rhumb line. So let's say I cut this meridian at an angle, which is theta. Next, I cut the next meridian also at theta. Next one also at theta. So this red line which you see is a rhumb line. It is a line that is cutting all the meridians at a constant angle. Now this line has a constant bearing from all the longitudes. It is a line which has constant true direction. Okay, so the true direction of this line remains always same. It is always pointing at the same direction because its bearing is the same from all the meridians. Perfect. Now a fact about rhumb lines is that the rhumb line spirals into the nearest pole. So if we look at this diagram also, you see how this line is spiraling towards the nearest pole, right? If I continue drawing it, you'll see that this ends up at the pole. So a rhumb line spirals to the nearest pole. This is a question which you can expect in the exams. And the other important thing is that it is a line of constant direction. Perfect. So Rumline was a line that was cutting all the meridians at the same angle. Now if I talk about more examples. So if you look at the latitudes, you would know that all these latitudes are also cutting the meridians at a same angle. And what is this angle? This angle is 90 degrees. So all latitudes, if I talk about this latitude, it is also cutting the longitudes at 90 degrees. So all latitudes or the parallels are also Rhumb lines. They are cutting the longitudes at the same angle, which is 90 degrees. Another example of the Rhumb line is the equator, because even the equator is cutting the meridians at the same angle, which is 90 degrees. So equator is both a Rhumb line and a great circle. Okay, examples of Rhumb lines are the parallels of latitude. They are also cutting the longitudes at the same angle, which is 90 degrees. Okay, let's now look at the definition of a nautical mile. So in aviation, the universal unit for distance is nautical miles, and 1 nautical mile is equal to 1852 meters. Okay, so this is an important conversion which you guys should know. Now, what is a nautical mile? So a nautical mile is defined as the arc of a great circle or meridian which subtends an angle of 1 minute at the center of the earth. So now you would ask me, what is 1 minute of an angle? So an angle of 1 degree is made up of 60 minutes, right? And if I ask you what is 1 minute, so you can easily apply the unitary method that 1 minute will be equal to 1 by 60 of a degree, right? It's just basic unitary method. If 1 degree equals 60 minutes, 1 minute would be equal to 1 by 60 degrees. Okay, so this is what 1 minute of an angle is. It's just 1 by 60th part of a degree. Now I'll explain the definition of a nautical mile, which I just said. So I want you to listen to it again very clearly. So I said that a nautical mile is defined as the arc of a great circle or meridian which subtends an angle of 1 minute at the center of the earth. So the arc of a great circle which is making an angle of 1 minute at the center of the earth is 1 nautical mile. So if this was a great circle on the earth and this is the center of the earth, now if I go on the surface of the earth and I measure an arc, so let's consider this arc. Now if this arc is making an angle of 1 minute at the center of the earth, then this distance will be 1 nautical mile. Do you understand? So 1 nautical mile on the surface of the earth is the length of the arc which is making 1 minute with the center of the earth. Okay, now you all know that the earth is an oblate spheroid. And this is what an exaggerated oblate spheroid will look like. Yeah? Flatter on the poles and bulgier on the equator. Now here if I take 1 nautical mile around the equator, it will be something like this. And if I take 1 nautical mile on the poles, don't you think that 1 nautical mile on the poles will be a bigger distance? And both of these angles will be equal. Both of these will be 1 minute. But since the earth is flatter on the poles, the distance of 1 nautical mile increases as this arc is bigger on the poles because of the earth being flatter over there. And this arc will be less on the equator because the earth is bulgier, right? So I want you to remember these distances now. So 1 nautical mile on the poles is equal to 1862 meters. On the equator, it is equal to 1843 meters. And around 45 degrees, it is equal to 1852 meters. And that is what we use because we want a middle value. we don't want the extreme values, right? We want a value that is an average. So between the equator and the poles, we have 45 degrees latitude. So we'll take the distance of 1 nautical mile at 45 degrees latitude, and it turns out to be 1852 meters. So for us, 1 nautical mile equals 1852 meters. So I hope you understood the reason why 1 nautical mile on the surface of the earth is also different. Because of the irregular shape of the earth. It's flatter on the poles. That's why 1 minute on the center of the earth is covering more distance on the surface of the earth. So I hope you understand this part. Perfect. So now I'll just write the important conversions related to 1 nautical mile. So I've already said that 1 nautical mile equals 1852 meters, which is also equal to 1.85 kilometers. Yeah, I can say it this way as well. And 1 nautical mile is also equal to 6080 feet. So you should know all these three conversions. Now let's move ahead and let's talk about what is 1 kilometer. Now we all have heard of this term called a kilometer, but we have never known the definition of 1 kilometer. So 1 kilometer is defined as the 1 by 10,000 part of the average distance between the equator and either pole. Now to be honest with you guys, this is the most stupid definition I've ever come across in aviation. So the distance between the equator and the pole is 10,000 kilometers. And they're saying that if you divide this distance by 10,000, you will get 1 kilometer. Like wow, what a discovery. So if you look at this diagram, it literally says that the distance between the equator and the pole is what? Is 10,000 kilometer. And in the definition, it says that 1 kilometer is the 1 by 10,000 part of the average distance between the equator and the either pole. So they're literally just dividing 10,000 by 10,000 to get 1 kilometer. And this is how they're defining 1 kilometer. Okay, so this definition can also be asked in the exam, but it's obviously very lame and very easy to remember. Now an important conversion related to kilometer is that 1 kilometer is equal to 3280 feet. So as a pilot, this is an important conversion and you should know it. Okay, so this was everything I'll be covering in the general navigation basics video. This was more of building the concepts, as I said in the beginning. So in the coming videos, I'll be talking about how to find the change in latitude, change in longitude, what is departure, what is convergency, and all those things. So if you have doubts in anything, if you find anything difficult, if you didn't understand something which I talked about in this video, just let me know. Just drop in a message, just drop in a comment. And as usual, thanks for watching. I'll see you in the next video.